In this video, we're going to look at inverse trig functions. We're going to understand and use inverse sine, cosine, tangent, as well as secant, cosecant, and cotangent functions. We're going to find the exact values of the inverse of these trig functions. We're also going to use a calculator to evaluate some inverse trig functions when they're not on the unit circle. We're going to find exact values of compositions with trig functions. Just as a review of what an inverse trig function or an inverse function is, first of all, for the function to have an inverse, it must be one-to-one. And you're like, I know that word, what does it mean? Well, it means for each output value, there's only one input value associated to it. What that means is this function must pass the horizontal and vertical line test for it to be a one-to-one function. What does it mean for inverse? Well, inverse basically says I have the answer. What did I put in it? Here's the definition. For any one-to-one function where f of x is equal to y, then f inverse of x, and this is f, this superscript of -1 is inverse of x, is a function of f, of the original function, if and only if my function inverse of y produces x. So I have the answer is my input. The output is what I had to put in my original function to get that out. This can also be wrote as a composition of functions, provided, of course, x is in the domain of the inner function. It also follows that in this composition, that x is in the domain of the inner function of the inverse. This is the inner function, is the inverse. The notation f inverse, it is read f inverse, it is not f raised to the -1 is not 1 over. It's not the reciprocal, it's the inverse. And remember, not all functions have inverses, at least not when we start out. We can restrict domains, though, to get some inverses. So what does it do for trig functions? What does it mean for a trig function to have an inverse? It basically says we are undoing. What are we undoing? Well, if the trig function, if you put in an angle, the ratio pops out. For the inverse, you put in the ratio, and the angle pops out. That's associated to that ratio. Provided, of course, we're using the correct domain. So we're always chasing the angle that produced that output. The input is always the ratio. It does not mean 1 over the function. Now it has to be one-to-one. So let's look at sine and let's restrict it. If we look at sine, the sine wave goes forever to the left of the origin, forever to the right of the origin. As you can see this line here, this line y is equal to b. If b is between -1 and 1, I'm going to hit my sine wave an infinite number of times. So we're going to cut the sine wave, just like we did in Pre-Calculus 1, in such a way that I get all the possible output values for a very restricted and smaller domain that allows us to be one-to-one. So I restrict it between -pi/2 to pi/2, but I get to include it. So from -pi/2 to pi/2. My range is still everything for the sine, so -1 to 1. That's my range, my y values. And now I can find the inverse of that. You can see that my original function is the pink curve here. My inputs were angles. My outputs were numbers between -1 and 1, inclusive. I'm going to include those. And this blue graph here represents the inverse function. Notice that I am putting in the ratios. So from -1 to 1, those are what gets to be put into my inverse, and the outputs are going to be angles between -pi/2 and pi/2. So when we see y is equal to sine inverse of x, that means that x, which is the ratio, is equal to the sine of the angle. X, my inputs, are from -1 to 1, and my outputs in inverses are -pi/2 to pi/2. Just as a note, you might see it wrote as sine inverse this way, or arc sine. Now let's talk about what we are in terms of quadrants, because this will be important, especially when we're looking at this information on the unit circle. Now we know from graphing that this is quadrant 4 with a negative rotation. This is quadrant 1 with a positive rotation. What does that mean? Well, when I'm on the unit circle, I'm going to go down in this direction to negative pi halves. Or on the unit circle, I'm going to go up in this direction to pi halves for the sine function. This is where it is going to be defined. So that means the sine inverse. When I'm doing this, I'm looking for ratios in these two quadrants. So I'll be looking for ratios in quadrant number 4 and quadrant number 1. This is really going to mess with you. We're going to mess with you even more. It's fine though. You'll get used to it and it'll be, oh, I got this. We also get this. Here's some more properties. So f inverse of f of x, the composition, is the sine inverse of sine, provided, will equal x, provided that this angle lies between these two values, so negative pi halves to pi halves. This is the one that makes us unhappy. This is the, oh, I'm not so happy one, because sometimes it works out and sometimes it doesn't work out. But this one here, where I've got the composition where the inner function is the inverse, this is my happy one. And the reason this is my happy one is because my sine, which is the inner function, is already restricted. So if my inner function is already restricted, this is always going to hold true. I'm not going to have to chase where I'm standing and bring it back to where I need to be. And this is going to be explained later when we start to actually do the finding these compositions. Now, if we look at the cosine, it also is not one-to-one. So we're going to restrict it. We're going to restrict the cosine so that it has every possible output value. And sure, I could restrict it from here to here. I could restrict it from negative pi halves or negative pi to 0. I can restrict it anywhere. But I want to restrict it around the origin because it just makes it easier. Life is so much easier when we're around the origin. So I'm going to restrict this between the 0 to pi, inclusive. So then here is the domain of my restricted sine, or my restricted cosine. The domain of my restricted cosine is from 0 to pi, inclusive. I get to include 0 and pi. And my range is from negative 1 to 1, also including negative 1 and 1. So here's what my restricted domain looks like. So when I go to graph these, again, my pink line, or my pink curve is my cosine restricted, and my blue curve is my cosine inverse. They always get reflected, inverses always get reflected over the line y is equal to x. So I know with the composition, f inverse of f of x, my inner function is the cosine, not the restricted one, so that's my sadness, because that may or may not work out. But when I have the composition in the other way, this one, this is my happiness, because it's just x and I don't have to chase anything. Now, in terms of quadrants, we're in quadrant number 1. We know this from graphing. This is quadrant number 2. We know this from graphing in our previous section, our previous chapter. Now, in terms of the unit circle, we are in quadrant 1 and quadrant 2. So quadrant 1 and quadrant 2. And this will be important. You've got to know where you're standing. I always say that all the time. Do you know where you're standing? Because that's going to determine what the answer could be and whether it's not. So if I'm looking for the arc sine of negative pi halves, remember, I only get to be in quadrant 1 and quadrant 4 with a negative rotation. So negative pi halves to pi halves. That's the only place I get to be. So I get my unit circle out. On my unit circle, let me see if I can go grab that unit circle because I think I've got it somewhere. I don't. Let me go grab a unit circle. Okay, so I got myself a unit circle. Now remember that if we're going in this direction, this is negative pi halves. And if we're going in this direction, this is a positive pi halves. This is quadrant 1 and quadrant 4. So I look for the answer or the ratio of a negative 1/2 for the y. That's this one. And I'm tempted to say it's 11 pi over 6, but remember I have to go in a negative rotation. So this is actually negative pi over 6. Because of that, my answer here is negative pi over 6. So negative pi over 6. Cosine is in quadrant 1 and quadrant 4. Quadrant 3. There we go, 3. No. Holy moly. Let's count this again. Try quadrant 2. Bam. That was difficult for both of us. I'm looking for, in quadrant 1 or 2, a negative 1/2 as the ratio for the x part, and that's this. So this is just 2 pi over 3. The cosine of 0. So I'm looking for the cosine of 0. I'm looking on my unit circle. Where is my x value equal to 0? That's at pi over 2. And it's only pi over 2 because that's the only place for cosine is in these two quadrants. I don't get the lower half of the circle. I only get quadrants 1 and 2. Now I'm going to look for the sine inverse of square root of 3 over 2. So I'm going to look, square root of 3 over 2 is positive in this quadrant, and I'm looking for the square root of 3 over 2 for the y value. So we know that that's pi over 3. Pi over 3. Now let's look at tangent. Again, tangent is not 1-to-1. We're going to have to restrict tangent. We like to restrict it around the origin. So we're going to restrict it with just from negative pi halves to pi halves. This tells me, without the fact that I don't get to include negative pi halves and the positive pi halves, it's going to have the same or similar, it's not going to be the same, it's going to be a similar restricted domain as sine. Sine and tangent have restricted domains that are similar. The only difference is that tangent does not get to include negative pi halves to pi halves because it's undefined there. It's my vertical asymptote. My range is different. For tangent, we get everything from negative infinity to infinity. And then, of course, when we look at our tangent graph, here is my original tangent graph. And I know this is kind of weird, right? This blue here, and I changed it to pink. I'm just changing it up to make sure you're paying attention. So my original function is in pink. My inverse function of tangent is in blue. You can see that my original function is constrained between negative pi halves and pi halves for the input, which means its output is going to be constrained between negative pi halves and pi halves. So let us now look at, oh, look, here's our happy and sad place. Here's some properties. Happy face, yay. The inverse is on the inner function. Sad face, the inverse is on the outer function. That's kind of sad face. We'll talk about that when we get to composition. So here's kind of a wrap up what we talked about in sine and cosine and tangent, where it depends on where we are. And this is where the sad face comes into place. If my inner function is just sine, and this is a composition, I don't get just x unless x happens to be in this interval. So if I'm asked to find the sine of 3 pi over 4, the answer here is not going to be 3 pi over 4 because 3 pi over 4 is not in negative pi halves to pi halves. Let's look at some cotangent stuff. So here's my cotangent. I restrict cotangent similarly to the cosine, going between 0 and pi, non-inclusive. That means its inverse, its range, remember domains become ranges, ranges become domains. This will have a range between 0 and pi for its inverse. Of course, with the other trig functions, we get cosecant and secant. Cosecant is the reciprocal buddy of sine, so it's going to be similar to sine, with the exception of where it would be undefined, which is at 0. The cosecant inverse, the secant inverse, it's going to be similar to cosine, because it's the reciprocal buddy of cosine, except for where it would be undefined, which is at pi over 2. So, if we're asked to find the exact value for x in which the interval of the inverse is defined. Now, this is different than finding all the values of x and make this true. This is asking for where the interval is defined. So once again, I'm going to grab my unit circle, and I'm going to make note on my unit circle where sine and cosine and all of those are defined. Tangent can go from negative pi halves to pi halves. So this is where I get my tangent. This is where I get my sine. This is where I get my cosecant inverse. Provided, of course, it's not undefined. Cosine is going to be in quadrants 1 and 2. So this is going to be for cosine inverse, the cotangent inverse, and the secant inverse. I've got to keep that in mind. Know where you stand. Sine is only in this blue area along this curve. And remember, we have to go not 3 pi over 2, but negative pi halves, 2 pi halves. And the green will go from 0 to pi. So if I have the sine of 1/2, I'm going to go look for 1/2. This is pi over 6. Bam, when x is pi over 6. Tangent. Where is tangent equal to -1? Only in these two regions. Well, that's where x and y are the same values with opposite signs. So you want to say it's 7 pi over 4, but it's not. It is a negative rotation. So it's negative pi over 4. X is equal to negative pi over 4. Because remember, this is a negative pi over 4 rotation. Negative pi over 4 is coterminal to 7 pi over 4. You're like, where am I ever going to use coterminal? Here. Here's where you're going to use it. Cotangent. Cotangent is in this green part. And a cotangent is like tangent. I need to have my x's and y's be the same with opposite signs. And this is simply going to be when x is equal to 3 pi over 4. I don't have to do any weird shenanigans with that. Secant. Secant is the reciprocal of cosine. It is positive. We're in quadrant 1. And this is when x is equal to pi over 4. Now, how do I know that? Well, if I wouldn't have rationalized these two, if I wouldn't have taken the square root of 2 over 2, if it was before it was rationalized, it was 1 over the square root of x, or square root of 2. And that means the reciprocal of 1 over the square root of 2 is just square root of 2. Similarly, here we go. Bam, cosecant. Cosecant is the reciprocal of sine. So I need to know which quadrant I'd be negative. It's a negative rotation down here. So I look over here and, they rationalized it on me. And I told you in my class, you never have to rationalize. So I'm looking for the square root of 3 and 2. It's this one. If I were to not rationalize this, this not rationalized would have been negative 2 over the square root of 3. It's so much easier if you don't rationalize, but it has been. So we know the ratio that produces that is a negative pi thirds. Remember, we have to go with a negative rotation here. It has to be a negative rotation. Here's some applications. Now these are going to be applications where we're working on right triangles. A truss or an interior beam structure for the roof of a house is constructed from 2 identical right triangles. Cool. Let's draw my right triangles. Bam, look at that. That's so perfect, isn't it? You're just like, wow, I'm in awe of your drawing skills. So am I. Each has a base of 12 feet and a height of 4 feet. Well, this is 12 feet, and this is 4 feet, and this is 12 feet, and that one's 4 feet. Find the measure of the acute, that's the one less than 90 degrees, adjacent to the 4-foot side. So in other words, what they're asking me for is this. They're asking me for that angle. Now that angle, in terms of sine and cosine x, y, and r, I'm going to take that triangle and I'm just going to tilt it on its side so that here is my right triangle. This is the angle I'm really concerned about. This is 12 and this is 4. Now, taking this angle this triangle, and basically what I've done is I've taken this and rotated it 90 degrees. That allows me to easily see that I have the x value and I have the y value. So if I have the x value and the y value, then I'm chasing this theta. So in other words, I want the tangent of theta to be the 12 over 4. And the reason I'm using this is because I have the y value and I have the r value. Now they want this, it doesn't say whether or not they want it in degrees or radians. And I can tell you what, for most people, it's going to be easier to do it in degrees. So the theta is going to be the tangent inverse of 12 over 4. What allows me to do that is if I take the inverse of both sides, just like when I used to take the log or natural log of both sides to solve for an exponent, I can take the tangent inverse of both sides. And I can use the fact that I know that the tangent inverse of the tangent of theta is equal to theta, provided theta, that's not zero, provided theta is in the appropriate region. So I'm just going to get my calculator out, and I'm going to calculate this with my calculator. I'm probably not in degrees, so give me a moment to go into degrees, because you know I'm probably not. Let me see. Mode, there we go. And I was not, I was in radians. So make sure your calculator's in radians. So in my calculator, I have a second key and then the tangent key, and that gets me the tangent inverse. And then I put in 12 divided by 4. So that tells me my theta, the one that I'm chasing, the one that's adjacent to or next to the 4, the one that's 4, is 71 point, and we're going to round to, let's go with 2 decimal places because I think I lost that. 2 decimal places, so 71.57 degrees. That's that angle. If I wanted to find this angle right here, then I know all the angles add up to 90. If I wanted that one, we'll call this one alpha. That means that 90 minus the theta would equal my alpha if that's the one I'm chasing. Let's take a look at another example. Suppose a 13-foot ladder is leaning against a building, reaching to the bottom of the second floor window 12 feet above the ground. And what angle in radians does the ladder make to the building? So here's my building, here's my ground, here's my ladder. This ladder is 13 feet long. It's reaching to the bottom of this window, which is 12 feet above the ground. The angle that we're chasing is this angle. I'm going to call it theta. So I look, and what I have is I have an equivalent x and equivalent r, or not x, y. I have equivalent y. So I am going to use the sine of the angle is going to be equal to the 12 over 13. That's because I have the y value and the r value. As before, if I take the sine inverse of both sides, then I'm going to get theta is equal to the sine inverse of 12 over 13. Make sure your calculator is in radians, because I know just a moment ago I used it in degrees. So I'm just going to go ahead and do this calculation, making sure that I am now in radians, because that's what they're asking me for. So in my calculator, I'm going to type in the second button, or the shift button, the one that has the sign to gives me sine inverse, 12 divided by 13. And again, we're going to go with 2 decimal places. So theta is equal to 1.17, well actually to 2 decimal places makes that 8 radians. Okay. Last example, really nice example. Now, all of these that I've been doing so far have been right triangle. We're going to go in our next learning objective will not be right triangle, but these both have been right triangle, and so will this. Suppose you drive 0.6 of a mile on a road so that the vertical distance you have drove changes from 0 to 150 feet. What is the angle of elevation on the road? So again, I'm going to draw my picture, obviously not to scale. They're telling me I have drove 0.06 miles, and they're also telling me this is 150 feet. Let's kind of important on this one to have my units. My previous example, I didn't really need to worry too much about units because of the fact that they were the same. But now I really do need to pay attention to the units. I'm going to still use the sine. I'm still going to say, okay, the sine of theta, this being the theta, this is the angle I'm chasing. Now, the thing I have to do, though, is I have this 0.6 miles. And I need to convert this into feet so that we are talking the same units. So I know there's 5280 feet. Yahoo, Mile High City, Denver. Call out to you all. 1 mile. That's how come I know it. Unless you live there. And then I'm going to just do the 0.6. So 0.6 multiplied by 5280. And I get 3,168. Now, again, it's my y value, which is 150. 150 divided by my r value, which is 3168. I'm going to take the sine inverse of both sides. This side and this side. And I'm going to get theta is equal to, it hasn't told me whether or not to use radians or degrees. I think I'm going to probably use degrees. It would make sense to use degrees. So I'm going to go into my modes. I'm going to make sure I'm in degrees this time. And I'm going to do my second or my shift button on the sine so I can do the sine inverse or the arc sine. And then I'm going to do 150 divided by 3168. And I get 2 decimal places is 71 degrees. So that is my angle of elevation. Now, I had talked about before the happy and sad. This is where we're going to be happy and sad. I want to evaluate the composition of functions. The first thing I want to do is always evaluate this inner function. Now, I know when I see the tangent inverse of -1, I am chasing some angle theta. Because if I see inverses, it says I have the ratio, and I'm looking for the angle that produces that. So once again, I'm going to bring in my unit circle. I'm going to use that a lot if it's on the unit circle, and this one is. Remember for my unit circle that tangent and cosine get to be in these two quadrants with a negative pi, so a negative rotation to pi. Those are the two quadrants. So I'd look to see in those two quadrants where the tangent inverse, in other words, where's the ratio, equal to -1. So I'm looking for the location in which my x and y values are the same things with opposite signs. It's right here. It is not 7 pi over 4 because I have to have a negative rotation. So this is negative pi over 4. So this is the sine of this angle, which is negative pi over 4. Because that's what the tangent inverse of -1 is. The tangent inverse of -1 is the angle. This angle happens to be negative pi over 4. So I've evaluated the inner function. Now I'm going to go and say, what is the sine? Now I'm just looking for the sine, not sine inverse. What is the sine of negative pi fourths? This is the negative square root of 2 over 2. So that's my final answer. Remember, every time I am doing the inverse function, my answer is the angle. The input is the ratio. The answer is the angle. Okay? So again, it looks like these are probably all on the unit circle. If I'm not certain, I'm going to go ahead and bring in my unit circle again. Bring in my unit circle. Cosine, I'll do that in blue. Cosine is in these two quadrants. So when I see 1/2, I am chasing where my x, or my x value is 1/2, so that's pi thirds. This is equivalent to pi thirds. So I'm really asked to find the tangent of pi thirds. The tangent of pi thirds is my y value over my x value. So in other words, it's the square root of 3. That's my final answer. Now, remember I said this is my sad face? Sad face. This answer is not 3 pi over 2. And the reason this answer is not 3 pi over 2, because here's where 3 pi over 2 is. Is that in my blue arc? The answer is no. It's not in my blue arc. So what I have to do then is I have to evaluate this inner function first. This inner function, the cosine of 3 pi over 2, is 0. So this is really asking me to find the cosine inverse of 0. So now I go to my blue arc, and I say, where on my blue arc do I see the x value equal to 0? And it's straight up, so that's pi halves. So that's my final answer. There's no other answer. That's it. This is my happy face. Happy face, and I didn't have sad face. This is my happy face. Because when it's in this form, when my inner function is the inverse, the answer is just whatever is right here. That is my happy face. And you're thinking, well, what about A? Well, if we take a look at A, tangent and arc cosine are not the same functions. So that isn't going to hold true. First of all, to be in the happy spot, they have to be the same functions, with the inner function being the inverse and the outer function being the regular function. This is not the same function. Yes, the inner function is an inverse, but it is not the inverse of tangent. Okay, now let's take a look at my last couple of questions here. And again, I'm going to use my unit circle, and I'm going to evaluate my inner function first. Arc sine, well, this is different. This is 1 over the square root of 2. And I said before in this class, you never have to rationalize. But if you decide to rationalize negative 1 over the square root of 2, if I were to rationalize this, I would multiply the numerator and denominator by the square root of 2. This gives me negative square root of 2 over 2. And this is more familiar. Remember, it is in these two quadrants that the arc sine is defined. So I look to see where I see the negative square root of 2 over 2. It's down here in this quadrant. It is not 7 pi over 4. It is a negative rotation. So this is equal to negative pi halves, or pi fourths, pi fourths. So this is the secant of negative pi fourths. The secant is the reciprocal buddy of cosine. The cosine is odd. That means the secant is odd. So this is the same thing as the secant of pi fourths, which is the same thing as the square root of 2. And that's that final answer. Oh, and that's this final answer. So I look at E, and E is my sad face, because 5 pi over 4 is right here. That is not in my blue arc. So I have to evaluate this inner function first, and this gives me 1. The cotangent of 5 pi over 4 is positive 1. So then this is the cotangent inverse of 1. So I look to see on my unit circle where in the blue arc is sine and cosine equal with the same sign, and that's when I'm at pi over 4, and that's my final answer. So we're either sad or we're happy. Worst case is you always evaluate the inner function first and then evaluate the outer function. All right, now this is going to be slightly different, and it's going to be joyous or not, depends on how you look at it. Remember, every time I am asked to find the arc sine, the arc cosine, cosine inverse, or anything like that, this is an angle. So we know that the arc cosine of 5 over 13 is an angle. That's true. So then if I take the cosine of both sides, which is before we took the cosine inverse. So if I take the cosine of both sides, I'm going to end up with 5 over 13 is equal to the cosine of my angle. So then what I really have here, this whole thing, because it is an angle, is theta. So that means I really am looking for sine of theta. I'm not actually chasing the angle this time. I'm chasing the ratio. And I'm going to use this to find that ratio. Cosine is my x value over my r value. So I know x is 5, r is 13, y is going to be the square root plus and minus, and I'll deal with that in a moment, plus and minus 13 squared minus 5 squared, which is going to be the square root of 12. squared, which is just going to be 12. It's because it's a 3, 5, 12. You were like, oh, I was so impressed. No, it's a 3, 5, 12. Okay. So now I have found the cosine, or the y value. Now, I originally had positive 5/13. The only time this happens with the arc cosine is in quadrant 1. So that must be, I'm in quadrant 1, so I just have the positive. The sine of theta is my y value over my r value. My y value is 12, my r value is 13, and there's the answer. And notice I didn't actually need the angle for any of it. Now I'm going to look at this one. This one's a little bit different. I'm going to ignore the 2 for a minute, and I'm just going to work with that. So I have the tangent inverse of 5/7. Tangent inverse of 5/7. That tells me that must be an angle because I'm always chasing an angle. That means all of this can be replaced with the theta. So what I have then is the cosine of 2 theta. So we know that if I take the tangent of this side and I take the tangent of this side, then I know the left-hand side is going to be 5/7 is equal to the tangent of theta. That tells me I have the y is equal to 5, the x is equal to 7, and r must be the square root of 5 squared plus 7 squared. Now this is where you're not going to be impressed because I have to get my calculator out. I don't know what 25 plus 49 is off the top of my head if it's something nice, and it's not. It's a square root of 74. Okay. Now, for us to continue, we'd have to know the double angle. We don't know the double angle yet, but we will. I'm just going to erase this so I can have the space. We don't know the double angle. We don't know what the cosine, how to get from cosine 2 theta to the angle that I really want. And because of that, I'm just going to have to ignore this 2. That 2 right there, I can't do anything with it right now. We will later. So for right now, I'm just going to say I'm not going to worry about the 2. I'm going to assume at this point it's a typo. So, because we haven't learned the double angle. So I'm really asking for the cosine. My cosine is my x value over my r value. Because tangent is a positive value, I'm taking the tangent inverse of a positive value. That means I can only be in quadrant number 1. My x value was 7. My y value was the square root of 74. And that is my answer for that one. Got a couple more. I was being all tricky, I guess. But guess what? We haven't learned the half angle, so I'm going to have to ignore that part too. So just assume that's not there. Just kind of squint and close your eyes, sort of, and it'll be fine. Focusing on this then I know the arc cosecant of 5/3 is equal to an angle. That means if I take the cosecant of this side and the cosecant of this side, I'm going to get 5/3 is equal to the cosecant of theta. Cosecant is the reciprocal of sine. This is my y, this is my r, this is positive. They're both positive, so I'm in quadrant 1 because I remember I'm chasing the arc cosecant. This is really the tangent of theta, which is my y value over my x value. So I need to find my x value. So x is going to be the square root of r squared minus y squared, square root of 25 minus 9, 16. So this is going to be the square root of 16. Square root of 16. This is going to be 3/4, and that is my final answer. And notice for all of these, I have not once have I had to actually find the angle. I'm not actually chasing angles this time. Let's take a look at my last example, and then we're going to do this generically. And this generically thing we're going to be doing is extremely important in calculus. Once again, we're going to say the cosine inverse of 1/3 is equal to some angle. I use theta. You can use whatever angle you want. Take the the cosine of this side, the cosine of this side. That gives me that 1/3 is equal to the cosine of theta. That means all of this is just theta. So what I really have is the sine of theta. I have this being my x, and this being my r. I am chasing y. It's going to be the square root of 3 squared minus 1 squared, my r squared minus my y squared. So I have y is equal to the square root of 8, which if I want to, I can write as 2 root 2. So then my sine, which is my y value, 2 square root of 2 over my r value, which is 3. And that is my final answer. Now, up until here, we've had either angles that were nicely on the unit circle. Worst case is they weren't, and I had to use my calculator. Or I had ratios with numbers. Now I don't have numbers. The same thing is going to happen then. The same thing. It's just we're going to treat it slightly different. The sine inverse of u is equal to theta. The sine of this side, the sine of this side tells me that u is equal to the sine of theta. I'm going to write this as u over 1. This is y, this is r, x is going to be the square root. We always take positive, we assumed positive when we're doing it like this, algebraically. It is going to be 1 squared minus u squared. I'm really chasing the cosine of, now remember this is theta, chasing the cosine of theta. Cosine of theta is my x value, which we just found to be 1 minus the square root of 1 minus u squared, over my r squared, which is 1, and that is my final answer. And before you ask, no, you don't have to put it over 1. You can, but you don't have to put it over 1. That's up to you. Okay, so now let's do some of these. I'm just going to give you the answers. Or actually, you know what? I'm going to do one more, and then I'm just going to give you the answers. This is theta, remember? So arc cosine of v is theta. So if I take the cosine of this side and take the cosine of this side, I'm going to get v is equal to the cosine of theta. It's v over 1. This is x. This is r. Y must be the square root of 1 minus x squared, or excuse me, v squared. Because this is really just theta, this is really just the sine of theta, which is just the square root of 1 minus v squared over 1, or in other words, 1 minus v squared. Now, I want you to do the last 3. We will absolutely go over these if you need to in class. So I'm just going to give you the answers. The first answer is just going to be 1 over the square root of 1 plus, and I script my s's because otherwise it look like 5. That's not a delta, that's an s. It's a cursive s. So that's s squared. This one is going to be 1 over the square root of 1 minus u squared. And this last one is 1 over w. And that's it for this video. We will see you in class. Make sure you ask good questions. And hopefully this has been helpful for you.